Students, title of today's lecture is Semiconductor Low Dimensional Systems, and today we are going to cover part 2 of this topic. In part 1 we learned several concepts about the low dimensional systems. Let's review those concepts which we discussed in the previous lectures before proceeding further. Now you understand very well what is nanotechnology. It is actually study of manipulating matters on the atomic scale, and when the dimensions becomes very small, this quantum confinement effects comes into picture. And we discussed that the quantum confinement is normally observed when the dimensions of the material they become comparable to de Broglie wavelength. De Broglie wavelength is given by this formula. Actually, at these dimensions, wave nature of the electron starts dominating. You have seen this kind of picture in the earlier lecture. So you can see this wave nature is dominating. This wave nature is visible when the electron is confined within the small dimensions, and it forms a type of standing wave pattern there. Another criteria you can say, or you can say the critical dimension below which you can say that this quantum effect starts dominating, that is exciton Bohr radius. Exciton is a type of phenomena where a electron, free electron and a hole remains in binded state, and they travel together inside the material. So when the dimensions becomes equal to the size of exciton, or you can say below the size of exciton, then this quantum confinement, or you can say the wave nature of the electrons comes into play, and then the properties of the material changes drastically, and the changed properties give rise to new kind of applications. In the last lecture we also discussed what are three different kind of confinements. So first is a 3D material or a bulk material you can say, then this is a 2D material, and then this is a one dimensional material where 2D confinement is there, and now the last one shown here is a 3D confinement, or you can say 0 dimension material, because it's confined in all the 3 directions. The free movement of carrier is not allowed in all the 3 directions. So this material is like a dot, and it is also known as quantum dot, and this is known as a quantum wire because the confinement is in 2 directions, and third direction the movement is allowed, and that's why it is called one dimensional material, because carriers can travel only in one dimension. And the concept is repeated here. The strong quantum confinement is observed when the size of nanocrystal is below the exciton Bohr diameter, and the de Broglie wavelength is also one criteria. So when the size becomes comparable to de Broglie wavelength, then we start observing the quantum confinement. Okay, so this is something which we are going to discuss today. We are going to discuss about 1D materials and 0 dimensional materials. 2 dimensional materials were discussed in the previous lecture. We will also discuss some examples of 1 dimensional materials and 0 dimensional materials. So let's have some discussion about the 1 dimensional quantum materials. So 1 dimensional material you can say, so the 1 dimensional nanostructures are actually nanowires. So they look like this. So this is one representation of 1 dimensional nanostructure, and here you can see the electrons or whatever carriers are there, electrons or holes, they can travel only in one direction. Other 2 directions they are confined because they are not free to move in those 2 directions. Now nanowires, or you can say these 1 dimensional materials, they are very popular these days, and they are attracting much interest from the researchers, especially those researchers who are trying to use nanotechnology in solid state electronics and diagnosis tool in medical sciences. These 1 dimensional materials are like quantum wires, and the quantum wires have very high conductivity, and you know in electronics or solid state electronics you can say, in order to connect the devices we need wires, And the quantum wires, since they have much higher conductivity, they can prove very useful, and not only just for making connections, but for acting as a active part of the device. For example, for implementing MOSFET devices also, the one dimensional materials or these quantum wires are being used. So now you can see some more applications or more concepts about the one dimensional materials. Unlike other low dimensional systems, nanowires have two quantum confined directions, x and y. You can say they are quantum confined directions, and carriers are not allowed to move in those directions, but one unconfined directions. We are talking about degree of freedom. So they are allowed to move in one direction only for electrical conduction purpose. So here you can see some examples. So in this first example, you can see this kind of structure is formed here on gallium nitride and sapphire combination of substrate, and that way you can see since they have unconfined movement only in one particular direction, and the dimensions of this tip, it is shown here with this color, and it is enlarged in this portion. This lateral width, we are talking about this red portion, this lateral width, that lateral width is very small, and it is covered with this black protective layer, and basically we are interested in this red portion, which is very small here. So this width, lateral width is very small, and that's why we are saying that the confinement is there in the x direction and y direction, but in this one z direction, so the free movement is allowed. You can see here another example, some gold and germanium alloy. The atoms of this alloy, they are placed next to each other in such a way that they form a line, and similarly there is a line of atoms of platinum germanium alloy. So atom by atom placement is done in such a way that the width of this wire is very small. It means the carriers, they are not allowed to move in other two directions, only in one direction along which their length aligns. That only in that direction conduction of electron is possible. So the third example, third alloy is also shown. So you can see the dimensions in the lateral directions, they are almost atomic dimensions, or maybe few atomic dimensions. That's why there are restrictions in lateral direction, and only one direction conduction is allowed. This is the reason that they are known as one dimensional materials. Now this kind of property makes these nanowires to be used in applications where electrical conduction rather than tunneling transport is required. Means we need to conduct carriers from one location to other location, and it's not that tunneling. Tunneling is a different kind of phenomena. It is conduction, and but since the dimensions are small, electrons are considered as a wave instead of as a particle, and we start observing quantum effects there. Now let's see some applications of one dimensional materials. For example, the silicon transistor, which is used in the integrated circuits these days in our computer systems or in electronic systems, that is going to be replaced by carbon nanotube based transistors. So you can see this kind of structure. You can see here on this substrate several nanotubes, they are placed here, and these nanotubes are going to work as the conducting channel, and there is a drain portion, there is a source portion, and then there is a dielectric here, it is shown here, and over this dielectric there is a gate. So these nanowires are going to be used as an active part of a MOSFET device. And since we are using nanowires, definitely we will have very small area occupied on the substrate, and the other parameters performance parameters of the MOSFET device, they are also expected to be very good. The carbon nanotube, which I was just showing here, this kind of tube, this is a one carbon nanotube. So that is actually a molecule in the form of a hollow cylinder with diameter of around a nanometer, which consists of pure carbon. So it is made of carbon and its diameter is about several nanometer, you can say. So the another example is shown here. So you can see the graphene sheet is there, and this particular light blue structure, that is one carbon nanotube, and here you can see this oxide is there, yttrium oxide is there, and on the top of this there is palladium. This palladium material acts as a gate. So that way a nanowire based MOSFET device is implemented. Of course, it will have quantum effects because the diameter of the nanotube is very small. Now, these kind of nanorods, they are being used not just for implementing MOSFET devices, but they are being used in many upcoming technologies. For example, in the display devices, and the reason for this is that these nanowire or 1D materials, they consume less power and they emit less heat. So these are some of the benefits which are offered by 1D materials, or you can say nanorods. They are also called nanorods because their diameter is of nano order. And because of use of these 1D material, or you can say nanowire or quantum wire or nanorods, whatever you prefer to call them. So use of them is giving us a major benefit, and that major benefit is that the size of the microprocessor is being reduced to greater extent. So it is extent, not D, this is extent, right. So size of microprocessor, that is being reduced by the use of these kind of 1D materials. Now if we talk about the allowed energy levels, because I told you that the electrons behaves as a wave, and if they are behaving as a wave, the wave function can be described by the Schrodinger equation. And if you solve that Schrodinger equation for 1D materials, for this kind of two-dimensional confined structure, then the allowed energy states, they are given by this. So you can see here this Kz. So that is like a type of like translate vector. So it indicates the direction in which it is free to move, and this Lx and Ly, these terms indicate that the movement is restricted in x and y direction. So here the nx and ny are quantum numbers, and they can have any integer 1, 2, 3, etc. right. Now after having this discussion about 1D materials, now let's start discussion about 0D, zero dimensional quantum materials. Means 3D confinement. The carriers are not allowed to move in all the three directions. It means they have 0 dimensions, and they are also known as quantum dots. Now 0 dimensional nanostructures are also called quantum dot nanocrystals. Generally, nanocrystal is a semiconductor crystal whose size is of the order of just a few nanometers, right. So here you can see one example. So this is example of one nanocrystal, or you can say 0 dimensional structure. This is of gallium arsenide material, and it is known as quantum dot because 3D confinement is there, or you can say it is 0 dimensional material, and it contains just 465 atoms, right. So when we talk about quantum dots, normally they contain anywhere from 100 to 1000 electrons, right, and they range from 2 to 10 nanometer, or if we talk in terms of atoms, their diameter may vary from 10 to 50 atoms, right. So here we are seeing total number of atom is 465, but if we talk about diameter, so diameter is like from one end to other end, and that may contain about 10 to 50 atoms. Quantum dots are unique. Why? Because of their size and properties, right. The size is very small, and because of this small size, wave nature exists there, and that gives a new kind of properties which are normally not present in their bulk form. Now, almost all material systems, including metals, insulators, and semiconductors, they show size dependent electronic and optical properties in the quantum size regime, right. So you have seen in the previous lecture also that when the size of this confined region changes, its band gap changes. So that is one property which is size dependent, and you know, the band gap decides many optical and electronic properties of a semiconductor material. It means at nano dimensions, when the carriers are confined in 3 directions especially, and you can say we are working with 0D materials, in that case, if band gap is changing with the dimensions, it means we can have new properties, optical and electronic properties. Sorry. So among these properties, some most important properties we are going to discuss. For example, modification in the energy band gap of semiconductor. That is the most attractive one because of fundamental as well as technological importance. So you saw that when we change the size, the band gap changes. This part we discussed in the previous lecture, and here you can see another example. Here we are not changing size. So what we are changing, you can see here one material. This material consists of 3 different elements: cadmium, sulfide, and selenium. So if we are keeping even the dimensions same, so you can see the dimensions are same. You can see this red one, you can see this yellow one. So the dimensions are same when we are when we are moving from one side to other side. The only thing which we are trying to change here is the presence of selenium, right. So we are increasing selenium when we are going from this side to this side. You see, when we are changing the amount of selenium in this material, then the band gap is changing. So this part have a small band gap, and this side we are showing comparatively large band gap. So that kind of band gap tunability is possible when we manipulate the composition of these kind of quantum dots. So you can see here the semiconductors with widely tunable energy band gaps. Tunable means we can tune the energy band gap, means we can change the energy band gaps. So the one example is here in case of this compound cadmium sulfide selenium. So this kind of tuning of band gap, that is considered to be a material for next generation flat panel displays, photovoltaic application, optoelectronic devices, lasers, sensors, and photonic band gap devices. You know, most of these devices are optical devices, and their optical properties, they are dependent on band gap. And since that band gap tunability we have seen here, that is a very interesting property, because we can get desired effect. And here in this you can see the efficiency and the current density. So the efficiency is shown is about 5.06%, and the current density, it starts from this particular value, right. So anyway, what we want to say here is that this band gap tunability, just by changing the composition of these quantum dots, that is very useful for getting the materials of next generation optical devices. Now the discovery of quantum dots has led to development of an entirely new category of materials for active regions of LEDs and laser diodes. So, LEDs you are using, laser diodes you are using. So, if we fabricate LEDs and laser diodes with the help of quantum dot materials, then we get very good response. For example, you can say indirect band gap semiconductors that do not luminescence in their bulk form, such as silicon, they become efficient light emitter at nanoscale due to quantum confinement effect. So, you know, silicon is an indirect band gap material, and when we talk about optical devices like LEDs and photovoltaic devices, we go to compound semiconductors, for example gallium nitride or gallium arsenide, because they are direct band gap semiconductor. So they can emit light. Silicon cannot emit light because it is an indirect band gap semiconductor. But interesting thing is that when we use silicon in the form of a quantum dot, means when we reduce its dimensions below the exciton radius, or when we make it comparable to, when we make its dimension comparable to de Broglie wavelength, at that time quantum confinement effects occurs, and uh, this material also starts emitting light, right? In bulk form it doesn't emit light, but in quantum dot form it emit light. So, that is one interesting property of 0D materials, that even indirect band gap semiconductor, they can be used to form a LED or other light or optical based devices. So, you can see here one structure of a LED. So, I hope that you are much aware about the working of LED. So, LED is formed by a semiconductor junction, and the recombination of carriers takes place in that depletion region, and the recombination produces light. And what is the frequency of light? That depends on the band gap of material. But here what we are doing, so you can see here these red dots are quantum dots, right? And on the top there is ZNO. This ZNO is also a dotted structure. So, there also quantum dots exist. So, these two materials, they are made of quantum dots, and when this type of combination is used, you can see on the top there is aluminum cathode, and on the bottom there is a ITO glass. So, they are electrodes actually. So, we have a junction here, and this junction is formed with the help of quantum dots, and this produces light. So, it acts as a light emitting diode, and the efficiency, you can see the efficiency is shown for 3 different colors, for green LED, for red LED, and for blue LED. And the efficiency is very good. Now, the study of quantum dots has advanced our understanding of emission mechanism in conventional LED materials such as indium gallium nitride, which is the active region of blue LEDs. So, blue LEDs was a challenge since last many years. It was difficult to form blue LEDs, but because of advancement in the technology, and because now we are able to implement, we are able to make 0 dimensional materials, we are able to make quantum dots, it has become possible to form blue LEDs, and blue LEDs normally are formed with the help of indium gallium nitride material. High radiative recombination efficiency of epitaxial indium gallium nitride is due to self-assembled and localized indium rich clusters that behaves like quantum dots, right? So, what you have to understand from this point is that it is possible to form indium gallium nitride based quantum dots, and the quantum dots which are rich in indium, right? There is more percentage of indium into this material, and since it is a quantum dot structure, it gives you very high radiative recombination efficiency. So, good efficiency is possible in case of indium gallium nitride material if we make it indium rich, and if we make it a quantum dot. Not only in LEDs and the other for optical devices, even for solar cells. So, if solar cells incorporates quantum dots, they may lead to more efficient light harvesting and energy conversion. So, you have seen that the use of zero dimensional materials, or you can say the quantum dots, can give you much better efficiency in LEDs, in solar cells, and in other optical devices. So, thank you very much. So, this is what I wanted to discuss with you, what I wanted to convey to you.